The worldwide prevalence of bone disorders has been trending upward and is expected to continue rising, especially in populations where aging is combined with obesity and poor physical activity. The risk of fracture and bone atrophy is especially significant among older populations, affecting 2 million Canadians today. Conventional bone disease treatments involve replacing the damaged bone with healthy bone from another site in the patient's body or from another person. However, both of these techniques require additional surgical procedures to harvest the healthy tissue. Synthetic bone scaffolds are being introduced to simplify and reduce risk in treating bone atrophy. Our project contributes to the ongoing discussion by providing structural comparison of 3 synthetic bone structures: truss, TPMS, and a topology-optimized design to assess their loading and failure behavior. The truss design is made of interconnected cylindrical beams, while the TPMS design takes the shape of a smooth, wave-like surface. The topologically optimized structure is designed with the help of computation. Unnecessary material is iteratively removed from the structure, leaving behind material in the most critical locations. The structures are designed with the same amount of pore volume as the human femur. The results indicate that the topologically optimized sample will yield the least, followed by truss, then TPMS. We 3D printed, then tested the compressive behavior of the structures. Results of mechanical testing validated what we saw in simulation, but we learned more about how these parts would break under extreme stresses. We found that although able to withstand the most load, the topologically optimized structure fails in a brittle, catastrophic manner. We recommend designing bone scaffolds with the truss structure, which can withstand less load, but is less prone to shattering in use. Our research to date provides a necessary and fundamental step toward identifying structural candidates for the next generation of bone grafts. The next step is to combine features of topology optimization with truss-type structures. This can be done by variably thickening the trusses in critical locations as determined by a topology optimization algorithm. Further improving bone scaffold design requires great minds from all corners of engineering and science. To read the full report and get involved in our research, please get in contact through the link below.